Our next presentation is actually an end user of the OPC UA technology from our vendors. Please introduce Clinton Chapman from Schlumberger. If I can find his presentation up here.
Well, thank you for the opportunity to come here and talk to you about what we're doing in OPC and drilling automation. This is a new area for the drilling industry. We don't automate very well, and it's really within the last few years that we had one of the leaders come from the nuclear industry and start trying to really push his sort of dream of what they were able to achieve in automation and pushing that on to into drilling and to do the automation. So I'm going to cover a little bit about my perspective about why I care about it and the organizations that I'm part of that push this, and then a little bit about drilling rigs and the organizations which use them, because it drives a lot of how we actually want to use OPC UA. Then why do we automate drilling, and architecture that was proposed for drilling automation, and then some results from the demo that we used to prove out the architecture, and this occurred in October last year. So from my perspective, I'm the drilling automation program architect for Schlumberger, and my job is to develop and integrate the drilling systems and algorithms together to optimize the drilling process, primarily just through automation. And then I also, in my volunteer job, is the Deputy Chairman and Comms Team Leader for the Society of Petroleum Engineering Drilling System Automation Technical Section. Yes, it's a mouthful. So its objective, I wanted to put it down here, and I'll just read this to you. So the objective of this group is to accelerate the uptake of drilling system automation by supporting initiatives that communicate the technology, standardize its nomenclature, promote lessons learned, best practices, and help define its value proposition. So some of that is actually this meeting right here to kind of tell you what we're doing and how we're using it for automation. So a little bit, what is drilling? What this shows is a drilling rig, and it has a BHA, which is a bottom hole assembly, which is this silver part here, that's drilling through some sort of formation. This one's drilling horizontally. Typically a well is somewhere between 3 to 8 miles long. The information from our measurements are taken downhole, telling it what the position is, the formation that is drilling in, some properties like that, and then it's communicated uphole. The rig sometimes transmits this across to a base where there are people sitting in various service companies or in the operator's office, and then they make decisions that are communicated back and then transmitted downhole. For the drilling rig, this is a very small drilling rig. It's called a rack and pinion rig. It's hydraulic when it operates. There's 3 main pieces of equipment on the mast, which this is a hydraulically controlled hoist. It lifts the drill string and the BHA out of the hole. And then it rotates by this yellow piece up here. This is a top drive system, which rotates the drill string and the BHA when it's on bottom. And then the hole is cleaned. So as you drill, you generate a lot of cuttings at the bottom of the hole, and you have to clean that out. So they pump fluid down the hole, and it goes down the middle of the drill string, cleans the cuttings, lifts it all up to the surface, and then also maintains the pressure that's downhole. So this is like what happened with BP Macondo. They didn't maintain the pressure correctly, and they lost the well. And so the mud does that operation. All of these systems are integrated back into this system here, which is the driller's console. And the driller's console takes these sort of disparate systems which come and go on the rig. So like they may change the top drive out and the PLCs and everything, and then have to reintegrate that into the system at the rig site in the middle of Mexico. That's where this rig is at, by the way. And so these systems can change, and so there's a lot of almost like plug and play which can happen at the rig site on these things. Another aspect is that this controls is there's an auto driller here which controls the rate at which the blocks move down to actually drill with. So part of the automation is that it can lower the blocks at a constant rate, or it can maintain a specific weight on the blocks, and what that means is that you're maintaining a specific weight downhole in order to drill with. The last thing, so you had these three main, really 4 main pieces of equipment. There's also a bunch of sensors which are scattered around the rig. One of these, for example, is a sensor which sits up here and manages the it monitors the standpipe pressure, which is how much pressure is actually being transmitted downhole. And what you can do is you can change and send pulses up through the pressure in order to communicate with your piece of your tool, which is about 8 miles away. All right, and I'll talk about that in a second. I'm gonna skip this slide. All right. So downhole, you also have a lot of things going on down there. So you have bits and hole openers. These are put down hole to actually construct the wellbore. There's motors and rotary steerable systems. This is a picture of a rotary steerable system, which it provides active control of the trajectory. So in order to do active control, somehow you have to communicate to it. Again, I spoke about the measurements. The rotary steerable system actually contains the capability of doing a direction of receiving the direction and inclination of the tool as it's going down there, and there's way of converting these single points from curvilinear coordinates into Cartesian coordinates, and a bunch of science around that. Formation properties, where you do gamma ray type ratings, neutron density, resistivity of the formations, which can take up at about 150 feet into the formation, for example. And then the telemetry. And this is where a lot of people are surprised, as so today the majority of work is done with mud pulse and e-pulse. And when you're talking about communication rates, you're talking about a half a bit to 18 bit per second at its very highest. If you're like not very deep, you might be able to get 18 bits per second. When you're very, very long, you're maybe a half bit per second, about how much data you can transmit up. Transmitting down, you transmit down at even a slower rate. It's usually about 1 bit every 10 seconds. And then the last part is wire drill pipe, which is new. I wanted to mention that. So this is a multi-magnitude change in the amount of traffic which can change. However, there's only 8 strings in the world today. It's very unreliable at this point. And we're hoping that maybe in 15 years there may be a reliable way of commuting at a high speed up and down the drill string. The last really important aspect of drilling automation that has to be considered is are the organizations that are out there. So the organizations are these 4 areas, right? So we have the operators who are really supplying the money to extract the oil. And then you have the drilling contractors who supply the rig and the personnel on the rig, and generally supply like the auto driller and all the integration points with the rig. The equipment suppliers who supply the pieces of the equipment, and these again like the NOV, CAN rigs, FDSs of the world, who come along and they supply like the top drive or the mud pumps or the auto driller, and then they work with the other systems to sort of integrate these things together. And then the service companies, so Schlumberger, Baker Hughes, Halliburton, these come along to supply the technical expertise and a lot of the downhole expertise on how to have all these things work together. And so you get this thing of cooperative adversaries who are working to extract as much money as they can out of the operators, okay, in order to drill the well. So why do we want to automate? So a lot of this is around the drilling better and more predictably. What this shows is the depth drilled. Okay, so they're starting at 1,400 feet, 1,400 meters, and going to 3,000 meters, and over amount of time it took to drill those sections, and we've compressed all the connection times, and this is just the downhole drilling on bottom rates. And the green rates are when automation was applied, and you can see that there's a tighter grouping, and so you can more predictably drill the wells in this area. And these wells over here were not drilled with any automation. So, and what we see is that there's a lot of inconsistency in those. There's a longer learning curve in trying to learn to drill the wells, and there's you have more problems. And what we're getting to in the industry is most of the easy oil is gone. And you're getting to the point where without automation, you're going to have to pull all the you're going to have to you're not going to be able to drill it without it soon. So okay, so moving more back towards OPC UA and why we use it. So the DSATS comp team was constructed about 1.5 years ago, and we've been deciding a protocol and tags for doing control, and then deciding the qualities and architecture that were going to be used to pull all these things together. We gave the demo at the annual technical conference and exhibition last October, and in the future we plan to do the detailed interface definitions and the commissioning test to pull these in. We chose OPC UA initially, and it was because of these benefits. There was components off the shelf were available, so the clients, the servers, the SDKs, the maintainability and setup is a big deal to us. So like the discovery, so you want to be able to take your laptop to the rig with your automation routines, plug it into the network, and it find out and be able to configure itself. The guys it's difficult to manage the IT infrastructure in the middle of Iraq, for example. The security model. Tag level control is very important to us. So you can imagine that when you have multiple systems connected to a rig, that you want this person to only be able to write to a specific set of tags and not the other ones which are writable. And then all the combination of the OPC UA capabilities, the classic OPC capabilities was there, compatible with many systems, like the G, FINOC, was it Iconics and WinCC, for example. And the last thing which was very attractive was the ability to apply an information model to it. So the WITSML, the Well Information Transfer Standard is the standard for drilling. It's been around about 10 years. It started actually around the same time OPC UA did, and so but it focuses on the interchange of information and is not as much real time as OPC UA is. And so we're hoping that maybe we can merge these two together to make a stronger drilling protocol. The architecture that was proposed, so you can see that over here we have the main pieces of equipment, the hoisting system, the top drive, the mud pumps, and some sort of generic piece, and these are all on the rig. These are sort of owned by the rig. There's a composite system which pulls these systems together in an HMI, and this is the driller's console that I showed in the third slide. So we've added a device called a comms device, which allows us to abstract this system, which is pretty well up to the rig, how they expose the components. The digital control to this device, which is a standard interface to the rig. It has an HMI with an automation control system that the driller would use. So he would have it next to him on the rig floor, and then connected to that would be external companies, which would come in and say this company could plug into the rig, and they would be able to say optimize the drilling on bottom process. Another company may come in and say, well, they're very good at tripping pipe, and they would be able to change these out. So you can imagine, like, if you want to on the manufacturing floor, if you were trying to do the same thing, what the issues you might encounter if you had somebody come in. I just want to plug my PC in and control your manufacturing equipment. That's almost like kind of what we need to do. The demo that we showed used a 3D simulator for the top drive. It was connected back to a drilling which provided an interface to this particular top drive. The comms device was here. It was a custom OPC UA server that was that the OPC Foundation generously donated a developer to come help us write. We used a Siemens WinCC SCADA system to connect to this, and Siemens generously donated time to put that in there. Then we had Shell, who came along and wrote these to OPC UA clients, which connected to the OPC UA device. And the objective was that the driller would be able to switch between rotating mode, which is you're rotating and drilling, and sliding mode, which is where you're trying to orient the BHA in a specific way to drill. Okay, so if you need to, you would just say turn right, turn left, go up, go down. This was all, these were just built in C#, C# clients, and then connected through here to control the rig. So the demo went perfectly. It was a great success. So in OPC, provided very easy access to get the tags and the real-time feedback, and writing the set points for the automation agents, the automation console, and it had the ability to customize the security model for the agent control and selection. So we would be able to say that this client could write at one specific time, and then we could switch that over and say now this other client could write, and nobody could overwrite what that person was trying to do at the time. It also provided sort of a user-friendly hierarchy of the equipment attributes, and so when you were setting this up, it was very easy to navigate this hierarchy and pull all of those systems together to be able to select and set up the OPC UA clients. So as a result of the demo, there were some changes that we were going to probably have to make, and a lot of this results is from that a lot of at least the off-the-shelf servers and SDKs didn't implement the full UA spec, and we were very lucky to have the OPC UA Foundation there to come and actually modify the custom server to get around the issues with some of the Java libraries that we were trying to connect to. So that was a bit painful to do. To relate to the legacy SCADA systems and the personnel who are developing, I think we have to, and maybe I can get some input from y'all on this, is I think we're going to have to cut back on some of the advanced OPC UA features that are available. The ability to put custom security in was probably not the best idea that we had, because it requires a custom-built OPC UA server in order to implement it. The use of web services, I don't see how we're going to be able to attach to generic web services that are exposed through using OPC UA from people who use SCADA systems today and are generally familiar with connecting to tags. And this, 10,000 tags, and they can connect and push all these things around. It's difficult to do. And the last thing was we're trying to determine the roadmap of the main OPC UA vendors and SCADA systems, and just to assure the availability of the advanced features. And the one big feature that we're looking for is this tag level control of the reading and writing of the individual tags. Okay, and that's all I have. Thank you. Okay.